To motivate skyline queries and also to see the difference to the aforementioned top K queries, let's have a look at this example. So what we see here is a screenshot from mobile.de website. So you see it's in German, but doesn't really matter. You see here the price of cars, and what I did here is to specify that the price should be up to 80,000 euro, and the first registration date should be between 96 and open-end. That means as new as possible is also okay. And kilometer, so the mileage, up to 125,000. And some other information, for instance, the zip code and the radius around the zip code. And you see the search engine then tells me that there are 48 hits to my query. So what are the results looking like? So you see here we have a Porsche, and this obviously qualifies with the certain constraints I have put, and another one and a third one. So we have 3 hits here. And how can we now compare these? So we see here that this one costs only 22,500, whereas these here are more expensive. Now we see that this one here has 103,000 kilometers run already, whereas this one here is much newer in this regard. So how can we compare now the first and the third one, for instance? It's difficult to compare them because this one here is really cheaper. On the other hand, it also has more mileage. So we cannot just say that now the third one is better than the first one. So we cannot really throw away one of the two options because they all look decent, and it's difficult or impossible to tell which one is better. If you're looking at the second one, we see that this one has a high price as well, like 24,999, and it's from year 2001. If you're looking only at the year and the price, and we're comparing this to the first one, we see that this one here is younger than this one, and it's also more expensive. That means here we also cannot really say which one is preferred over the other. This depends on the preference we have, how we can understand which one of these criteria is more important than the other. The point here is that it's really difficult to make a ranking because we have these conflicting domains like mileage or first registration date, and we cannot just sum them up like in top K queries. And of course you see there are also other criteria, like for instance the horsepower or the kind of machine it is. Here is like a benzene one, not a diesel one, and also the consumption of gas by 100 kilometers and so on, CO2 emission and so on. So you really see that this is like a difficult task, and we will see how we can define, how we can prune away the result set to a smaller amount, and this is exactly what skylines define. In another example, we have here a screenshot from the Mensa. It's from 2015, but you will see, if you're looking at the description here, that this will look very familiar to you. It seems they're not changing the kind of dishes too often. But anyway, it's fine, it's good, right? So let's have a look at this example. So you see here that we have different ways to assess these dishes. For instance, we have here, first of all, the price they cost. So you see that the spaghetti bolognese is like €2.15, which is of course cheaper than the other options. If you're looking at the number of stars they have obtained, you see that here the wok, like so this Pfannkuchen, the pancake, got quite good ratings, but it's also more expensive than the spaghetti bolognese. But you cannot say which one is better, because how would you aggregate into a final ranking the information about the price and the ratings? It's difficult. In addition, you see here that we have for the wok 36 reviews, and here we have 72. So the number of stars given here could be seen to be more reliable because there are more voters on this one. So you see here, for instance, that the Flammkuchen here costs €2.40, so it's more expensive than the spaghetti, and also it is not worse in the ratings than spaghetti. In this case, we can say, well, we should go for spaghetti because it's cheaper, and the ratings are the same as for the Flammkuchen. If we look at the review number, then we cannot really say which one is better, because then this Flammkuchen has much more ratings than the spaghetti bolognese. So you see, it's like a bit complicated. And of course, there are also more factors you can come up with here. For instance, what is the length of the queue? So the waiting time, the time you have to wait in order to get to the food. Even if something is really tasty and very cheap, there might be a huge queue, and maybe there's also some of these criteria you might want to take into consideration. So you see, the more of these criteria you have, the less likely it will be that one of these dishes is better in all ways than another one. And only in this case, when one dish, in this case, is dominating, as we say, another one, and then we can throw away the other one, otherwise not. And this creates, of course, a little bit trouble, because the more of these dimensions criteria we have, the more objects qualify to be not removable. The typical scenario that is often mentioned in papers around skyline queries is the following. You want to find a hotel. So you want to find a hotel which is like not really expensive, and it's also quite close to the beach. Let's say we have here meters to beach. Now let's have a look if you have a hotel which is 100-meter distance to the beach and costs €100 per night, and the other one is 150 meters away and costs €80. So let's say we have the red one here, and the green one should be, let's say, here. So which one is now preferable? This is not an obvious decision, because you cannot just sum up the meters and the dollars, right? So you can, then you have some numeric value according to which you can sort these objects. You cannot do that. So this is like something that in the end you have to decide, and that's why also these search engines like this mobile.de, they give you so many outputs to your queries, because it's difficult to make a final decision, or like a ranking of these. So now let's have a look what happens in another way. So if you had like a hotel, let's just make this up, a blue hotel, which is very close to the beach, and it's also cheap. So you see here that this blue one is better in all dimensions compared to the green one and the red one. So the green one and the red one don't have to be considered. And the skyline consists of all these points that cannot be thrown away. Another example, want to buy a car as before, and we have one which costs €10,000 and has 150,000 kilometers run, and the other one is €8,000 and has 130,000 kilometer run. In this example, that's easy because this car here is cheaper and has less kilometers compared to the other one. And unless, of course, we come up with more criteria, in this case, the decision is kind of clear. So the concept behind skyline computation is to have a set of objects with known characteristics, and it's not possible to sum up or to aggregate these characteristics into one final score that we could use to create a top K list of these objects. So it's not possible to come up with a aggregated score. However, the objects which are clearly outperforming others, like this car, for instance, that was cheaper and has less kilometer on it, these objects that are outperformed can be thrown away. And the ones which remain, these are making up the set that we call skyline. And the outperforming here, this concept we call here in the topic on skylines, dominance. We talk about objects being dominated or objects not being dominated. And then the skyline consists of all objects that are not dominated by any other object. The concept of skylines is also related or has different names. For instance, maximum vector problem, Pareto optimality, or also preference queries. For instance, here we have the paper from 95 talking about the maxima of a set of vectors, and then the one that made it famous or popular in more recent days regarding how skylines can be integrated into the computation in a relational database, specifically also introducing an operator that is like can be embedded or can be part of SQL in order to express skylines. There's little problem with skylines, not only how we compute them efficiently, we will see that later on, but first of all, as already motivated by the mobility scenario where we have these different criteria, if you have the number of criteria, like the number of dimensions of these objects getting very large, in the end you end up having almost all objects in the skyline. Because there's always like one dimension that avoids that an object can be thrown away. So if you're looking at, for instance, at mobile phone contracts, there's so many dimensions like the free SMS, the free minutes, the gigabyte of data volume, the kind of mobile phone you're getting, the number of months, runtime of the contract, and so on. So it's really difficult to make up your mind which one is the best. So you cannot just say or easily say that one contract is much worse or much better, right? One costs more, but then you're getting also more gigabyte volume. So it's really like at some point there's so many criteria in your so many number of dimensions, it's very difficult or almost impossible to throw away some of these. So what does it mean in theory? Well, if you have n data points and d dimensions, then the expected number of points contained in the skyline is growing like this. So the logarithm of n to d minus 1. So if you have like one dimension only, it's clear that you have one object in the skyline because there's it's a clear way to compare these or to rank these. Here you have two dimensions and you see that the expected number of skyline points for 100 objects is already 4.5. And if you go to 3, we have 21. So a fifth of these 100 points are in the skyline. This means that 3 is not a really large number, right? That means if you have 100 cars and you have 3 criteria, like dimensions, as we say, then you have 20 cars left. So the pruning power of this, like dominance or this idea of skylines is limited. And if you're going to 4 dimensions, then you have 97 cars remaining out of 100. So then that means in the end, pretty much all of the cars or all of the points are within the skyline. So let's have a look how this is formally defined. So we have a data space D of small d dimensions, d1 to dd, and we have a data set S with n points. Each data point we can describe by coordinates for the individual dimensions, and we also need to specify for each of the dimensions which one is better, to have a large number of the first one or a small number, or if these dimensions or the numbers in the dimensions are not comparable, which is this one here, will be also clearer in a minute. So how is skyline defined? The skyline is a set of data points that we call sky of S, which is a subset or equal to S. And the skyline contains of points which are not dominated by any other point. And these points are called skyline points. Not dominated means, or the concept of dominance means, you have a point P, and this point P dominates another point Q. We write like this: P dominates Q if for each dimension P is larger or equal to Q in this dimension I. And at least in one dimension, P is strictly better than Q. This is for the case of looking at that maximum numbers or larger numbers are better than smaller numbers. Right? That means like if you're looking at horsepower and first registration date of a car, in my eyes, both is better if it's larger, horsepower and the registration date. In this case, you would say a car is dominated. For instance, if the registration date is larger, so that means the car is younger, and the horsepower could also be the same, but one is enough. So if it's like in horsepower the same, then the registration date should be larger, so younger, or the other way around. Of course, it can also happen that it's both in strictly larger. That's also fine. So there should be one dimension where the one that is dominating is strictly larger, and for the others it has to be larger or equal, for the case of max. For the case of min, it's just the other way around. Smaller or equal, and in one dimension, strictly smaller. And here we see that in different words. You can of course combine min, max and diff. And since diff is a bit funny, or a bit like unusual, let's spend some words extra here. So by diff you can specify whether an object cannot be compared to another object by one dimension or multiple dimension. This means that an object cannot dominate another object if the attribute value in this dimension you're specifying with diff is not identical. This is used or important for scenarios where objects are not comparable if an attribute is not identical. For instance, if you're looking at mobile phone contracts and you see a contract is cheaper and has more volume, but then you see that this one dimension that is not comparable is the provider. For instance, if you have Vodafone or Telecom or O2 and you cannot really compare these, then you can say that one contract from Vodafone, which is cheaper and has more volume than the one from Telecom, still you cannot compare these because the provider is not the same. Or the mobile phone you're getting, one is Apple, one is Android. How can you compare now two contracts based on volume and the price if the phone you're getting is like incomparable? Unless you're imposing maybe your own preference that Apple is better than Android phones, or that Telecom is perhaps better than O2, right? But that's a different situation then. But in general, this is difficult to compare, so you cannot compare that. So you would put, in this case, a diff for the dimension phone type, or for instance, in this case, provider. On the left side, you see for some sample points the situation where small values are preferred. So then the skyline consists of these 2 points. And you see, for instance, this point here is dominated by that one. Of course, they have the same dimension or the same value for the second dimension, which is 1, which is fine. But here, of course, the 2 is strictly smaller than the 9. So we can eliminate this one from our skyline set. If you're looking at smaller values are preferred, then the skyline has a shape like this. If you're looking at larger numbers preferred, the skyline has a shape like this. So you see here, of course, this should be going through the green points, right? So you see that here we have the same situation. Now 6, 10 is dominating 1, 10. 10 is the same, well, but 6 is strictly better, larger than 1. So we can eliminate this. And of course, here for these ones, it's even more obvious to see that they are dominated by these green points. To further illustrate the concept of dominance, we can illustrate this or can imagine this like the following. We have one point. Here we have this green point. And this green point is spanning, in this case, of course, smaller values are preferred. This green point is spanning a region, and everything that falls into the region is dominated by this green point. And the same, of course, for the red point and the blue point. And everything that falls into these regions needs to get eliminated from our skyline because they're not part of it. You can generalize the concept of skyline into so-called sky band, where there's a parameter k, and the sky band consists of all points that are not dominated, or that are only dominated at most k-1 times. Since we have here a parameter k as well, again, note the difference to top k algorithms. Here we don't have any aggregation functions. Like for the normal skylines, it's the same concept. There are no aggregation functions. We cannot aggregate into a final score and just take the top k documents. Here, the k skyband consists of more than k. Usually, I mean, if the dataset allows, there's more than k objects. The skyband faces the same problem as the skyline. If the number of dimensions grows, more and more points are added to the skyline or to the skyband. And this is even worse here for the skyband because of the relaxation of this dominance definition. So you see here again, smaller numbers are better. The k skyband for k equals 1, so that's equal to our skyline. And if we're now increasing k to 2, you see more and more points are added, and to 3, more and more points are added, and so on. Now, how can this be expressed in SQL? Well, it cannot be expressed in SQL right away unless we integrate a new operator, and this was proposed by this very famous paper, the skyline operator, already published in 2001, where the authors proposed like a new operator in SQL that is expressing the skyline conditions. Of course, we will see that later on. It's also intuitive how to do this. We can express skylines in SQL even without that operator here, so it's only syntactic sugar. But this makes it, of course, easier to write than if we had to use normal SQL. But still, it's possible to express skylines also in SQL. That's important. The skyline operator is executed after select from where, group by, and having. But it is executed before order by and limit. So we have select from where, group by, having, and then we have the skyline operator. Here we specify for the individual dimensions min, max, and diff. And we have already seen what that means in case of min, max, and diff. And the only thing which is new here, or like different, is that we have here a distinct operator, or the notion of having this distinct option. And the reason is that objects that have identical values in all dimensions, so duplicates, will be returned as the result, unless we have the distinct command here, and then only one arbitrary one of this group of identical objects is returned. And for the sake of completeness, here you see from the paper the definition of the skyline operator, and here you also see what we have here assumed for the case of diff. There's a slightly different definition compared to what we have defined earlier in the slides, but this is only relevant in case of duplicates. So let's have a look at this example using the skyline operator. So we see here we want to get from hotels those which are not dominated by any other hotel in the city of Nassau. And we're doing this for the skyline over price and distance. And naturally here we say that it's better if the price is smaller and the distance to the beach is also smaller. And this would create our skyline result. Here below we have a bit more complicated query. Essentially it's just joining an employee table and a sales table, out of which we can compute for the name of the employee and the salary of the employee, the sales volume this employee is responsible for. We restrict ourselves to the year 1999. We do this, of course, by group by, like a typical SQL aggregation query. And now finally we say skyline of the salary and volume. And now you see here we're specifying the minimum to be better. So smaller values are better for the salary and larger sales volumes are better. So what does that mean? When is one employee now dominating another one? Well, one employee is dominating the other one if he or she earns less than the other one, but has a higher sales volume. And of course, in case of the equality of salary, then the volume has to be larger, strictly larger, and the other way around, just as we defined it in the dominance definition. Of course, we can also write this using standard SQL. So how do we do this? Well, first of all, we have the same predicate for the location. So we want to have city equals Nassau. From the hotels table, we obviously want to get our data from. And now reconsider, what does it mean for a point to be in the skyline? A point is in the skyline if it's not dominated. And in SQL, we say that a point is in the skyline where, or in case it not exists, a hotel which dominates this other hotel. How do we write that? So we have the hotel H, and there should not be any hotel H1, whereas H1 is from the same city, Nassau. And the distance of H1 is smaller or equal to the distance of H. And the price is smaller or equal than the price of H. And now importantly, there should be one of these two which is strictly better. So either the distance is strictly smaller than the distance, or the price is strictly smaller. And in case there is no such H1, H will be in the result. The naive way to execute this is using nested loops. And this, of course, can be very expensive in case the queries, for instance, would also contain more complex SQL, like joins or group by, which in this case is not the case, but the other one, for instance, the other example from before, was more complicated to execute. But the concept is the same. The trick here is to just realize again that a point is in the skyline if there's no dominating point, and this is just done by this not exists. So a point is in the skyline if not exists one point that is dominating this point. So let's see how this works if you have some sample input data. Here we have cars with a certain ID and a price and a mileage. And then we just walk through the computation. So you're comparing, of course, pairwise, and you're eliminating those which are dominated. And the ones you cannot eliminate are staying in the table. And then you're producing in a nested loop fashion the result. Since we know that nested loop is not really efficient, others have picked up the idea of skyline operators in database systems and have come up with different, more efficient ways. For instance, an approach based on divide and conquer principle, where you're splitting, as in this illustration, you can see the data space into different partitions, and you're computing in a distributed way the skyline for the individual partitions, And then you're combining the skyline points for the individual partitions, and you see here, for instance, that in this partition there cannot be any skyline point because the points would be dominated by the skyline points that you found in partition S3 and so on. This paper here is a good read if you want to learn more or get a good overview about skyline queries and efficient computation, because the beginning of this paper is very, very illustrative. So let's have a look at a concrete algorithm for skyline computation, also from the aforementioned paper. And we want to make use of data structures that we know already in order to find out which are the points which are dominated by other points without scanning the entire data set. And we will do so by looking at a skyline algorithm based on nearest neighbor search using R trees that we've seen already how that works. So here we assume price and distance, and you see here we have the skyline points A, I, and K. How do we compute this using nearest neighbor search in an R tree? Well, to start, we compute the nearest neighbor, and the query point in this nearest neighbor search is the origin, 0, 0. And then it's guaranteed that the nearest neighbor to this origin point is a skyline point. Here we have point I, which has a distance, an L1 distance of 5. So 3 plus 2. Then we know that the shaded area is dominated by the point I. And all these points within the shaded area can be disregarded because they cannot be skyline points. So they are pruned away. But we are still not done yet because there's also regions here which are not shaded. And as you can see here, of course, A and K are skyline points, so you have to find them as well. The idea here is now to create regions. In this case 1, 2, 3, 4, and we have already seen that 4 is done. We don't have to look at this. We're doing this region creation by the point I that we have just looked at. And I has the coordinates Ix and Iy. So we're creating two ranges here. And the first partition here contains regions 1 and 3. So this is this range. And the second one contains 1 and 2. And these partitions here are inserted into a queue, into what we call a to-do list, and will be looked at next. And as long as this to-do list of partitions we have to investigate is not empty, we take a partition and apply the algorithm to it. The point A that we already saw earlier by looking at this example is in the skyline. This point A is identified by performing a nearest neighbor search in the partition that is specified by these ranges here. So between 0 and Ix on the x-axis and 0 and infinite on the y-axis. So this region here, right? And if we're executing nearest neighbor search on this region, we will find point A. Hence A is also a skyline point. Now we take A, and like before, we look at these different slices, so the different partitions on the x and y axis, and we get then accordingly the range 5, or the ranges 5 and 7 here, and likewise 5 and 6. And we again insert them into the to-do list, and we do this operation until we are done. There's no partition anymore in the to-do list. And of course, in the first step, we have also inserted this one here into our to-do list. And when it's about time to look at it, and we do a nearest neighbor search, then we will also find this point K. And we are done if this to-do list does not contain any more partitions which can deliver results, and our algorithm can terminate.